law of gravitation, and that so using these two laws we can set up the equation for this problem, and it can be solved exactly. Now looking at the solutions, there are three kinds of solutions that show three different qualitative behaviors. Okay, first we can call it scattering trajectory. So this is the case when, let's say, some body comes in from afar. So initially it will move in straight line, and as it approaches the sun, the sun will bend the trajectory of this object. It will accelerate due to the force, and it will bend like this, and eventually it will go apart. So it will go very far, escape from the sun, never to return back to the sun. Okay, so this is called a scattering trajectory. The other kind of trajectory is where the body spirals in. Let's say you throw in a body and it has a mechanism to use energy, then it will keep falling towards the sun. It can take the path will depend on how the energy is lost and so on. But typically it will spiral inside and eventually hit the sun. And the third kind of trajectories are the stable bound orbits, where the body moves in a periodic motion around the sun in elliptical path. Okay, so this is what is seen in the Earth-Moon system or the planet-Sun system. Okay. Now what we will do is we will study the same question in presence of a black hole. Okay, so to study black holes, we need to go to Einstein gravity. So solving Einstein's equation of motion, we get a black hole solution. Now this black hole solution displays a new feature which is called as an event horizon. Okay, so basically event horizon is a sphere in 3 dimensions. So here we have drawn a circle here. It is the projection of that sphere onto the plane. This is the event horizon associated with the black hole. And at the center of this event horizon is a very small patch where the entire mass of the black hole is concentrated in. Okay, so it should be noted that there is nothing, no matter or anything here. It's just some a sphere associated with the black hole. We will see why it is special. Okay. Now, first, let us discuss the behavior of. Let's ask the same question again. Let's introduce a small body in vicinity of this black hole. But first, we will restrict ourselves to be outside the horizon. Okay. Then there is no difference. There is no qualitative difference at all. The behavior of the gravitational effect felt near the black hole outside the horizon is very similar to the gravitational effect felt near a star. Okay, so we will have scattering trajectories where particles will come in, they will get bent, and then they will escape. Then some object would form a stable orbit, elliptical orbit around the black hole and keep orbiting the black hole. Also, we could have a third kind of trajectory where particles spiral in. Okay, they will cross the horizon. Now, once the particle or any body crosses the horizon, then there is a difference. Then this scattering kind of trajectories don't exist. None of the trajectories that are present inside the black hole can escape this event horizon. So all they do is spiral back towards the mass of the black hole. Okay, so just to appreciate this point better, let us consider accelerated observers. So we will compare it with the normal situation. Let's say we sit in a rocket and just throw ourselves towards the sun, and we don't need to switch on the engines. The sun will just pull us towards it, and we'll just freely fall towards the sun. Now we are really falling inside the sun. At any point in the trajectory, we could switch on our engine and turn the rocket and head at the direction away from the sun and totally escape away from the sun. Provided we have engines of sufficient capacity, then it is possible to accelerate ourselves away from the sun and escape. And this can be done at any point at any distance away from the sun. But the same thing cannot happen in the event horizon. No matter how much you try to accelerate your object, you cannot escape from the event horizon. Okay. Yeah. So uh, now using this information, we can try to ask what would be the image of a black hole. Then it is simply nothing because it's just dark. Nothing can escape from this event horizon. So there is no emission and will not get a photograph. But so this is for bare black hole. In the universe, the black holes that exist, they don't exist in isolation. So let's see what happens. So most of the black holes are surrounded by some kind of matter, some dust or star. So what black holes will do is, due to their extremely strong gravitational forces, they will pull the matter near them in towards them. Okay, so here is a star, and so this black hole is pulling the gas or the matter of the star towards itself. Okay. Now, since this incoming matter, it will have some angular momentum. That's why it doesn't fall radially inside directly, but it has a tangential component and it rotates before spiraling inside. Okay. So this produces this disc-like structure around the black hole, and it is called as accretion disk. Okay. So now, because of the extremely high gravitational force of the black hole, this particles or this matter in the accretion disk, it moves at an extremely high velocities. And that's why mostly it exists in the form of plasma, where the charged components of the usual matter, electrons and the ions, are separated. And that is why there is a huge radiation coming from this type of motion. So mostly these objects show large amount of X-ray or other high energy kind of radiation. Okay. Yeah. So this is what most of the black holes in the universe look like. There is a black thing which is related to the event horizon of the black hole, and then there are accretion disks which are formed as the black hole pulls other matter towards itself. Okay, so this is what would be captured in the image. Okay. Now to understand how the image of an accretion disk is formed, we need to understand a little bit about the behavior of light in the vicinity of the black hole, outside horizon. Of course, we know nothing can escape once it goes inside the horizon, but in this vicinity, let's try to understand how light moves. Okay. Now we are observing, this is the black hole. We are observing it from here. Okay. Now let's say there was a light ray coming from here. Then normally it would just pass out like this in a straight line. And it's impossible for us to observe it from here because it will just pass like that. But due to the presence of the black hole, this light is deflected, and there's a chance that it might come into in our field of view. Okay. Now, near the black hole, the situation is even more drastic. Let's say you have a light ray that is escaping here. Now, we should remember that we're looking at the black hole from this direction. So, this is the back of the black hole. In principle, the backside of, since it's opposite to our line of sight, that shouldn't be observable to us. But let's say some light ray, if it escapes, it's emitted from this point, then it is deflected all the way like this, and it reaches us in this direction. So what we see is that even if something is happening behind the black hole, then it is possible for us to see due to this huge deflection, gravitational deflection created by the black hole. Okay, so let's say if you have an accretion disk here, then firstly you would see the direct radiation emitted from here, not the normal radiation. But on top of that, the accretion disk which is behind the black hole, that would emit some radiation, and even that radiation would move in this path, and it would be visible to us on the top of the black hole and on the bottom of the black hole. Okay. So this leads to an image like this. So yeah, so this resembles the image in the movie Interstellar. So we'll see, now we have an idea of how this comes about. So we are looking at the black hole in a particular angle. This is the plane of the disk. Okay, so we are looking at it face on. That's why it is almost like a line. Okay. Now, so the this part of the disk, it is visible because of direct emission that reaches us. Now, similarly, the other part of the disk is behind the black hole. The light coming from the upper edge of that disk, that will be deflected upwards, and it will come outside the page towards us. Okay, that is what forms this bright disk image of the bright disk above the black hole. Similarly, the light emitted from the lower edge of the disk, that will be pulled downwards by the black hole, and it will come outside the page towards us, and we will see an image of the disk below the black hole. So there is the matter is present only in this plane, perpendicular plane of the accretion disk, but the same matter forms this image over here on the top and on the bottom. There is no matter there. Okay. Yeah. Now let's say we are observing the black hole at a different angle. So this is the black hole, this is the accretion disk, and this is the observer. So he is observing this accretion disk at a particular angle I. So just to compare with our previous slide, there I was 90 degrees. We were observing the black hole from this angle. Okay, and then we saw this image due to direct emission. This part of the ring was formed the image above the black hole, and the lower part of the ring formed the image below the black hole. Okay, that was the special case of this but of a particular eye. Now let's say we have I equal to 0. We are looking at the black hole from the top. Then we will see an image like this. These rings would be visible as this. So this black portion is it depends on the event horizon. There is nothing coming out from there, and this ring is formed due to this accretion disk, and we are looking at it from the above. Okay. Now at an arbitrary angle, it will be a combination of these two things. Okay, so what we see from here is that the image of a black hole is mostly characterized like this. That there is a black region in the center, which is called as black hole shadow, and there are some ring-like structures around this shadow. The exact structure of these rings depends on the angle at which we are looking at the black hole. Okay. Yeah. Okay. Now, on top of this, we need to incorporate some additional phenomena that are happening around the black hole. So, as we discussed earlier, the material which is accreting around the black hole, that is highly energetic plasma. So, the net charge of the plasma is 0, so there are no electric fields involved, but still there are huge magnetic fluxes. So, we need to incorporate the effect of a magnetic flux. On top of that, we need to account for Doppler shifts, relativistic beaming, etc. So it's not important to know the exact meaning of these things. What I want to convey is that the intensity profile of the rings, how much power is radiated by the rings, it depends on lots of factors associated with the accretion disk and the black hole. Okay, and so actually, including effects of all these things, it's not even possible analytically. So we give this to a computer based on some particular model, and then it tells us how the image will look like. Okay. So what we have seen from this discussion is that the black hole image is expected to have a ring-like structure with a shadow in between, and the intensity profile of this ring structure, it is dictated by all such factors. Okay. So conversely, the question that we could ask once we have the black hole image, we could look at the intensity profile in the black hole image and try to understand how the accretion disk, what are the properties of the accretion disk of the corresponding black hole. Okay. Yeah, so now we will go on. Are there any questions? Yeah.
Hello. Yeah, so my question is, you spoke about black holes attracting stars from around them and creating accretion disk. So, is there an end to a black hole, or does it exist perpetually? Like,
Yeah, so classically, uh, the, a black hole will exist forever. But once we include quantum corrections, then the picture changes. So black hole can actually radiate. Yeah. But so this black holes can collide and merge and do all sort of things classically.
Accretion disk planar and not surrounding the black hole from all sides like a globe.
Yeah. So uh, so most so this is related to conservation of angular momentum. The matter that involves and the black hole system that has a total angular momentum, and that has to be conserved this since it is an isolated system. So when the uh, particles falling in the beginning, they can take any uh, path, but due to the collisions, they will keep on losing momentum. And since the total angular momentum about points in some direction, it can lose momentum such that the angular momentum has to be the same. Okay, so this results in a plane-like structure. So any component that was perpendicular to this, that has been lost by collisions. So that initially it would be arbitrary, but after enough collisions, then the matter always settles down into an accretion disk. So yeah. What happens?
The entire matter which is neighboring the black hole gets engulfed in it. What can we still observe it if there is no matter around it to revolve?
Oh, so you're saying there is a bare black hole?
No disk.
Yeah, just a black hole.
Yes,
Then it is not observable at all.
but that is a possibility that it can happen.
Yeah, it can happen. Yeah.
So every single imaging that we create with the disk, there is a possibility that after a definite amount of time that will not be observable because the disk will be gone.
Yeah, yeah. If the entire matter spirals in, then we cannot see it. But mostly what happens is there are always stars around it. So in on top of the accretion disk, there are stars that keep orbiting around the black hole. Okay, and they keep losing energy and coming closer towards the black hole. So so other stars keep on falling inside the black hole. Typically, that's what happens. Okay. Yeah. So there is a question answer. Yeah, yeah.
So I have a question related. I have a question related to dark energy and black hole. Recently, I read an article that
Yeah, so
the particles will merge.
can we keep it at the end?
Sure.
Yeah. So right now, let's have questions which need to be answered for the continuity of the talk, and other questions we will have a nice discussion at the end of the talk.
Morning.
Hi. Yes.
Hi. I have a question like when the star collapses, all right, and then forms into a black hole, what is the impact on the, I'm assuming that this particular star has its planetary system,
Okay.
right? So what impact now the black hole has on the planets that are there around this particular star?
Yeah. So so mostly what happens in an actual collapse, there are lots of other processes involved. There are explosions. So for example, if the sun goes into the red giant state, then it will already expand a lot, and it will consume some of the inner planets already, even in that stage itself. Yeah. So I think, do you want a scenario where this doesn't happen? Like, is that? Yeah, yeah. Yeah, yeah. So, in a hypothetical scenario where there is no expansion or anything like that, let's say the star just forms a black hole. Okay, then as long as the whatever things are outside the event horizon, they won't know it.
With the mass does decrease, right? The star had its own mass.
No, the mass is the same. Yeah, yeah. So the core. So after the after the supernova explosion, you had a core, right? So that entire mass is collapsed to extremely small, almost a point. That leads to an extremely dense object. Yeah, yeah.
Ma'am, can you repeat the electric and magnetic field part?
So sorry to interrupt. These are really amazing questions, but we are sort of on a time wave right now. So if you just let Sayali finish her talk, and we'll take all of the questions at the end of the talk so that it will be easier for us. Thank you.
Yeah. So next, now we have an idea like how the photograph of a black hole should look like. So next we will discuss a little about the telescopes involved in the imaging. Okay. So first thing to note is that the black hole, both the black holes M87 and Sagittarius A, they were imaged in the radio spectrum. In particular, the M87 black hole, it was imaged at 1.3 millimeter wavelength. So it is important to keep in mind that the colors displayed in the black hole image, they are fake. They are not related to any wavelength. So the entire image is at a particular wavelength, which is given by this 1.3 millimeters. It is not in the optical, so we cannot see it. It's in the radio spectrum. And so what the color in the image it is used to signify the intensity profile. What is the difference in the radiation emitted from different structures of the ring? Okay. Now, why was this wavelength chosen? So as we discussed earlier, there are lots of the black hole is surrounded by lots of stars and things like that. Now, these stars have their own. They are orbiting, they are losing energy and doing things like that. So they emit their own radiation. So the radiation from the black hole is contaminated by the other kinds of radiation happening around it. Okay, so this wavelength was chosen because the stellar systems around the black holes don't emit at this wavelength. Okay, so one can isolate the black hole signals at this wavelength. Now, radio sources are typically imaged using a technique called very long baseline interferometry. So, now if we want to have a telescope with high enough resolution power, then we need to increase the diameter of the telescope. Okay. Now, what happens for radio waves is that the wavelength of the waves is comparatively bigger. So if we just to compare, if we have an optical telescope and a radio telescope of same dimensions, then the resolving power of the optical telescope is much larger because its wavelength is much smaller. So for radio telescopes, we would need to make very big telescopes, and that is not possible practically. Okay, so what scientists do is that they use array of telescopes. This is an array of radio telescopes where each of this white dot is a telescope. So these telescopes have been arranged in this Y-shaped pattern. Okay, so what this technique uses is, let's say there is some radiation emitted from a particular source, then there at a particular time. Then it will not reach this telescope, all the telescopes at the same time. There will be a time difference, a path difference from because this telescopes are at different orientation and at different distances. Okay. Now, when the radio waves hit the telescope, then they are converted into electrical signals, and the electrical signals at different telescopes, they have a phase difference because which is related to the path difference in the light signals that come at the telescope. Okay. Now the information about the source is encoded in this phase difference. That's why what is done here is that people study the correlations between the voltages measured at different telescopes. And using these correlations can be used to reconstruct the image of the source. Okay, now I don't know the exact details of the process, how to reconstruct the information from the data available here, but there is a talk today on GMRT. So GMRT is this kind of telescope. So we will learn more about it then. Okay. Yeah, so the distance between a telescope is called the baseline. Okay, so that decides the resolving power of the telescope. Now let us try to understand what is the required resolution. So that we can see the black hole shadow present in M87 black hole. Okay. Now it is known that the emission ring of the black hole, M87 black hole, that is about 4 micro arc seconds. So to compare, to see how small this figure is, let us consider an example. Let us consider a tennis ball of 6-7 centimeters and place it on the moon. So that tennis ball on the moon would have an angular size roughly of 38 micro arc seconds. So the telescopes that we need, they should be strong enough to resolve a tennis ball placed on the moon. That is the kind of resolving power we need to see a black hole shadow. Okay. So this to have an resolving power of 40 micro arc seconds, we need telescopes that have baselines of about the diameter of the Earth. Okay. So keeping this in mind, the Event Horizon Telescope was assembled. So this is a global wave of telescopes where 8 telescopes have been are placed in 6 places across the world. So here you see they are very far apart. Almost the baseline here almost approaches the diameter of the Earth. That is what we need to process to obtain the black hole image. Okay. Yeah. So data was collected at all these 6 places, and then it was brought together and compared. So we as we discussed earlier, we need to understand the correlations between different locations. So the data had to be compared with one another in between the 6 telescopes, and that was used to reconstruct the black hole image. And so the analysis of the data also took a lot of time, almost 1.5 years or something. Okay, so finally we come to the photograph. This was the photograph produced after doing all that. Yeah, so to be completely honest, it looks a little bit boring. Like over 300 scientists, the smartest people in this world, they work on something for almost 2 years. So you would expect it to look a little bit more interesting than that. But this is what it is. Yeah, but I hope that you like the physics behind this image and find it interesting much more than the appearance of the image. Okay, so this is the black hole shadow. So first thing to note is that this has a ring-like structure, though it is blurred, but it has a ring-like structure. There is a black hole shadow in between. And just to have an idea of the parameters, so this black hole has mass of about 6.5 billion solar masses. That is the solar mass is the mass of the sun, and it is approximately at a distance of 53 light years away from us. Okay. Okay. Now, next thing that we could ask is, how do we use this image? How do we use this data to find new physics happening at black hole, and try to understand some parameters of the black hole? Okay. Now, the black hole, in this case, it is described as something called a Kerr solution, and it has 2 parameters. One is the mass of the black hole, which we have discussed, and another aspect is that this mass is rotating. The black hole is rotating now. So it has another parameter, its angular momentum, and that is described by its spin. Okay. Now, we will try to understand how we can estimate both these parameters from the black hole picture. Okay. Yeah. So one thing that I think I forgot to mention is that this black hole shadow it is not exactly the event horizon. It is actually larger than the event horizon. So why is it? Because if we look at the photon orbits near to the event horizon, then they are then the photons moving in this region, they are again pulled back inside the or inside the black hole. That's why they cannot escape. So actually, this black hole shadow is not probing exactly the event horizon, but it is a little bit bigger than that. Okay, and yeah. So another thing that I would like to mention is the relation between the size of this shadow and the mass of the black hole. Now, let's say some accretion, there is some accretion and some matter falls inside the black hole, then the mass of the black hole increases. So, along with the increase in the mass, the event horizon of the black hole would also increase, and the size of the black hole shadow would also increase. So, what it means is that the size of this ring, the emission ring, it is proportional to the mass of the. So here I have just written the quote from the paper. It is proportional to the mass of the black hole. Okay. So from this image, the size of this ring gives us an idea of the mass of the black hole. Okay. And but the exact details, they depend on lots of factors. It depends on the spin vector of the black hole, its inclination, the structure of the emitting region, the accretion disk, and lots of other things as well. Okay, but typically the size of the ring structure is proportional to the mass. Okay, now the second aspect of the image that we see here is the asymmetry. Here it is pronouncedly seen that the lower part of the ring is brighter than the upper part of the ring. So here the color schemes are such that this has more intensity and this has less intensity. Now this aspect of this asymmetry in the ring structure, it is related to the angular motion of the black hole. Okay. So this is visible from these pictures. So here, what these pictures are produced using computer simulation. So here, people used some model for the accretion disk, some very simple models, which involves just ionized hydrogen. So you just have electrons and protons moving at high velocities around the black hole. That is the model for the accretion disk. And then the value of A tells you the angular momentum of the black hole. A equal to 0 is non-rotating black hole. And so along this, we have increased the spin of the black hole. So what we see from this image is that in absence of rotation, the intensity of the ring is uniform. Okay. And as the spin of the black hole increases, then there is a sharp variation in the intensity of the photon ring that is seen from here. Okay, so here this arrow represents the spin of the black hole projected onto the plane. Okay, so what this means is, if we consider the lower edge, then the velocity, it is moving outside the plane. On the other hand, this upper edge is moving inside the plane. So the black hole is rotating like this. And if you use the right hand rule, that will tell you that your angular momentum has to point in this direction. That is what is meant by this arrow, the spin arrow. Okay, so the black hole is moving like this. And this difference in the intensity, that is expected once you include this motion. So the part that is moving towards us, there the intensity is enhanced. And the part that is moving away from us, there the intensity is lower. Okay, so this asymmetry in the ring, that it tells us about the spin of the black hole. Okay, yeah. So that's what I wanted to. That's almost what I wanted to say today, and I will just summarize whatever we discussed. So we discussed that black holes have a peculiar structure called the horizon. Okay, then we tried to see how the black holes in our universe they look like. We saw that due to the presence of matter around the black hole, they form accretion disk around them. And we also discussed what would be the image of such an accretion disk. And there we saw that it leads to ring-like structures in the black hole image. And this exact structure of these rings, it depends on various factors like the angle at which you observation at which you are observing the black hole. Then there are lots of other factors like what is the accretion disk made up of, what are then relativistic beaming and all those kind of things. But we saw that universally black hole image consists of a black hole shadow surrounded by some ring-like structure. Then we discussed how what is the angular size of the M87 black hole, and we needed something like the Event Horizon Telescope, which consists of radio telescopes spread across the all over the world to resolve this kind of size. Then we discussed once we saw the image, we tried to understand how it is related to the mass of the black hole and how the asymmetry is related to the rotation of the black hole. Okay. Yeah, so thank you for listening.
Thank you so much, Sayali. I thought that normal photography was difficult, but photographing of black hole is way more difficult than that. So we are actually running a bit short in time. So we will take as many questions as we can for the next 2-3 minutes. So just shoot. I think we have one over there. No? Over here.
Can you repeat that electric and magnetic field part of black hole? Hello?
Hi, yes. Yeah, so that was about the plasma. Okay, so what we discussed is that the gravitational field near the black hole is extremely strong. So the particles move at extremely high velocities. At those velocities, the electrons and the ions are separated. And we have a plasma. So the total charge of this plasma is still zero. So electric field does not play much of a role. But corresponding to the motion of the plasma, there are huge magnetic fluxes associated with plasma. And those play an important role in evolution of the accretion disk. Okay. Okay, we have one more here. You said that the wavelength region in which this image was taken was in the radio wavelength because that pertains to the black hole. So is there any other wavelength region where the image can be taken, or we can just take the image? Yeah, so black holes emit in lots of spectrum, and there are typically X-rays associated with accretion disk, etc. So why this was chosen? Because there is not much contamination from other sources. In all other wavelength regions, there would be contamination. Yeah. Yeah, near to this region, I'm sure. I'm not sure about. Yeah, mostly I think that's yeah. We can.
Hello. Yeah. So it was a very nice talk, first of all. And I have a question related to event horizon and particle which can travel faster than speed of light. We all know that if light particles goes in an event horizon zone, it can't escape. But what if the particle is faster than speed of light? For example, tachyons. Since tachyons are a hypothetical, but suppose we assume that
those could escape.
Those could escape the event horizon.
Space-like trajectories. Yeah.
So
only final objects moving on time-like trajectories cannot escape the event horizon.
So it can even pass through the event horizon as well. It can go inside a black hole and travel backward in time as from a different frame.
Yeah.
Thank you.
So there was one question that we had interrupted earlier. Yeah.
Am I audible?
Yeah.
So my question is related to dark energy and cosmological coupling of black hole.
Cosmological?
Coupling. I read a recent article that a black hole will later couple into the space-time curve and there will be expansion of universe. So is that physically possible?
Can you repeat your question? So our universe is expanding because of the cosmological constant. Okay,
Yes.
that has nothing to do with coupling with
No,
any black.
like the black hole will
Hmm.
later couple with the space-time curve and there will be expansion of universe.
So are you saying that black hole will affect the cosmological constant?
Yes.
Yeah, so there would be interplay, like you could try to also study the effect of cosmological constant on a black hole and vice versa. So because of Einstein's gravity, everything couples to one another. Okay, yeah. So it would back react.
Also, one more question. There exists a non-singularity black hole.
So classically, using Einstein gravity, we always get a singularity. But it is expected that once you include the quantum corrections, then that singularity will go away. That's why today in the talk I said I didn't say a point. I said that it is localized in a very small region. So it is expected that this small region would be of order of Planck mass, and at that order, certainly the quantum effects of gravity would come into play, and it is expected that it would somehow regularize this singularity.
It was a nice.
Thank you.
Okay, we have space for one last question.
I've heard that black holes can evaporate. So can they evaporate completely?
Yeah.
Like
Yeah,
how
so
do they
once-
evaporate?
Yeah, so that happens via something called so that is a quantum effect. Now we were just discussing classical, and once you include quantum corrections, then there is something called Hawking radiation. So basically, entirety of the black hole can just evaporate into Hawking radiation.
Okay, so my question is that are there any ending of the black holes? What will be the next step, next phase of the black holes?
Yeah, so classically, these solutions are stable, but as she was saying, that if you include the effect of quantum corrections on black holes, then the black holes also radiate quantum mechanically, and that would eventually lead to a process called black hole evaporation, where the black hole completely evaporates.
It will be completely blank, right?
Yeah, so but there would be some radiation.
Maybe.
Yeah, so something it will not be nothing. All the information of the black hole will go into the radiation.
Thank you.
Okay, that's all the time we have, unfortunately. If anyone has any questions, you can shoot us an email on